Okay, today we'll study a new topic, which is differentiation. After we have made a review, or we have studied several elementary functions, we have studied the trigonometric functions, the algebraic functions, which are power functions, and also we studied the exponential function and their inverse, sine inverse, cosine inverse, or inverse trigonometric functions, and the exponential function and this inverse, which was the logarithmic function, and so on. Also, you have studied the hyperbolic functions and their inverse, which were the inverse hyperbolic function. These are the elementary functions that we use along our journey in Faculty of Engineering. We will use these functions as elementary, or as a tool for expressing or modeling the systems that we are studying or analyzing. Okay? Now, let's just start with a new topic, which is differentiation. What is differentiation? Differentiation is the study of change. Now remember that our curriculum, or this what we are studying here, is called a part of called calculus, a part of mathematics called calculus. What is calculus? It comes from the word calculate. What does it calculate? It calculates the change between two variables. The change between two variables. What is meant by that? I may have a relation between two variables. All the functions that we have studied is a relation between two variables. For example, when we studied fy is equal to f of x, there is a relation between x and y. Whenever you change x, you get a new y. So this is a relation between x and y, a relation between two variables. Now we need to specify or give numbers that gives specifications of that change. For example, I may have a change like that. For example, that change may represent, for example, the change of a position of car. I have a car, for example, like this, and its position is x, and that position changes with time. That position, whenever the car moves, it changes its position with time. So that is depicted as x as a function of time, and there is a relation between the position and time. Okay, now if I had a relation between two variables that is like this, and another relation which was, for example, was like this, what is the difference between these two? What is the difference between these two relations? What is the difference in the change? I need to specify the change itself. As you see here in this example, the change is fast. What is meant by change is fast? Whenever I make a little change in the input or in the x, I find a large change in the output. Whenever I make a little change in the input, I find a large change in the output. So that is called a quick change. The change is fast in this case. But for example, in this case, the change, is it quick here? If the change is fast here, or is it slow? I see here the change is slow. Why is it slow? As you see, the change, as you make changes in the x or in the input, you find that the changes are extremely, you may see it as negligible, or something that is not a wide change, not a large change. Whenever I have made a large change in x, I have found a low change or a small change in the output. So that is a low change, okay? Or that is a slow change. That is a fast change, and that is a low change, or a slow change. Also, we may specify the change by its direction. What is meant by that? For example, I may have a change like that. That change is fast. It changes dramatically. As you see here, it is fast. The change is fast. Okay, but what is the difference? This also depicts a fast change. But what is the difference between these two cases? In the blue case, the change is increasing. As you see here, whenever you change x as increasing, the y also increases. But what about this case? Whenever you increase the x, what happens to the y? Whenever you increase the x, the y goes less. So it becomes less and less, but more quickly. So this function is decreasing. This function is decreasing, but this function is increasing. Okay? So this is a specification of that change. This is some kind of a specification. We call it the direction of the change. So we call the change positive change. We call the change a negative change. Okay? So what is meant by a positive change? It means that the change is increasing. Whenever you make a change in x, you find that the output is increasing. And when the change is negative, we mean that it is decreasing. So for this case, for example, I have a slow change, but it is decreasing. So if I want to find, or if I want to specify numbers to these different cases of changes, okay, in this case I will say, for example, this is a quick change or a fast change. So I may give it a large value. For example, I give it 100. Okay, I give it a number, for example 100, and I give it a positive value, so that I indicate that it is increasing. But for this case, I will give it also a value of 100, a large value. But what is the difference between these two cases? This case will be negative. Yes, we consider this as negative. So whenever I find a negative sign in depicting the change, we say that I understand that this function is decreasing instead of increasing. This function, we find that the value of the change is or we call it the rate of the change, as it is the speed of the change or the rate of the change. The speed here is slow, so we find a low value for that change, which is, for example, I give it 0.1. But what is the sign of that change, of that rate of change? Is it positive or negative here in this case? In this case, is it positive or negative? Is it increasing or decreasing? It is decreasing, so I give it a negative value. Yes, a negative value. For this case, the function is slow but increasing, so I give it a positive value but a low value for the rate of change. Okay, so what are these numbers? We call it the rate of change. And that is exactly what we are studying. What is differentiation? Differentiation is studying or evaluating or finding the rate of the change. How quick do you change? Okay? How quick do you change? So how can I measure exactly that change? How could I give these numbers exactly? Okay? Now, how to calculate the rate of change? We may do that by finding the ratio between the difference of the output to the difference in the input. What is meant by that? For example, if I had some function like this, okay? If I had some relation like this, and we have here for x, there is an output y, and I would assume that there is a difference delta x. So what would be that number? It would be x plus delta x. Okay? Now this is called y, or I may say this is called y is equal to f of x. Now what about this number? What is the image of this number? If I give that as the input to the function, what would be the output? It would be f of x plus delta x. Okay? So I may notice here that I have a difference also in the output, which is y. And so that that's why I will call that output, I will call it y plus delta y, as if this is y and this is delta y, so this number would be called y plus delta y. Okay? Now, how would I evaluate or measure, or how would I measure the rate of the change? How would I measure the rate of the change? When would the rate of the change be high? For example, for this case, if I made a small change in the input, I found there was a large change in the output. So it is the ratio between the change in the output to the change in the input. That is what measures the rate of the change. That is what measures the rate of the change. It is the difference of, or the change in the output related to or divided by or as a ratio to the change in the input. Okay? So for example, if I had a large value for this, it means that whenever I have some change in x, I would have a large change in y if that rate of change is high. Okay? Now, to make the measurements more accurate, it would be better to make that delta x, to make it as less as possible. To make it less as possible. And that's why we make delta x to be approaching 0. We make delta x approaching 0. What is meant by delta x approaching 0? This is a new kind of numbers. Do you know the science of calculus? That science was built up by Newton and Leibniz back in 17th or I think 2016. I don't remember the date exactly, but it was Isaac Newton and Leibniz who had the credit of inventing that science of calculus. What was the difference between Leibniz calculus and the other scientists who never? It was a known problem to find the rate of change, but any scientists before them didn't find the way such that they can measure the rate of change. What was the difference? The difference was a new concept that they have invented that wasn't considered before them. What is that concept? That concept is called the infinitesimal. That is a new concept. It is called the infinitesimal. What is the infinitesimal? It is just the opposite of infinity. So what is infinity? What is infinity? Infinity, it is not a number. It is something that is dynamic. It is a number that is moving. It just keeps moving larger and larger. Keeps getting larger and larger. But it is not something that is stable. No, it is. So I don't consider it as a number, and I don't treat it like other numbers. For example, if I had, infinity minus infinity, could that be 0? No, that is not 0. Why? Because these infinities are not numbers, are not stable numbers. They are dynamic. So I may have an infinity moving faster than another infinity. I may have an infinity moving faster than another infinity. So the difference between them would be large. Okay? So this concept of infinity is that it is not a number. It is another concept different from numbers. And so is the opposite of infinity, which is called infinitesimal. What is an infinitesimal? An infinitesimal is a number that its value keeps getting less and less, but never goes to 0. But it is never 0. For example, what is infinitesimal? It is 0.00000 and so on, then 1. Okay? But it is never 0. But it keeps getting less and less. such like the infinity. It is much like the infinity. It is a dynamic number, not a stable number. Okay? So that concept was new to the scholars back then. That concept was new, and that was the key idea that made Isaac Newton and Leibniz invent the science of calculus. Okay? So what are we doing here? I'm telling you that I would let delta x to approach 0. What is meant by letting delta x to approach 0? I mean I would make it less and less, but it is never 0 exactly. That means I need to make it infinitesimal. I need to make that delta x to be less and less, make it infinitesimal, but not 0. And infinitesimal is not equal to 0. It is, it is approaching 0. Okay? In this case, when I do that, when delta x is approaching 0, we give it a notation, we call it dx. So whenever you see that notation dx, dy, it is meant that that variable is, we take it is, we suppose or assume that this number is infinitesimal. Okay? We know that this number is infinitesimal. Okay, so if I consider that delta x to be infinitesimal, what would happen to delta y? It would be also infinitesimal. Whenever you make that to be much less and less, that output also will be much less and less. So that output will also be, in this case, if you made that to be infinitesimal, the change in output will also be infinitesimal. It would also be infinitesimal. So that's why, what is the exact rate of change at a point? What is the exact rate of change at a point? We call it dy by dx. We call it dy by dx. Why would you call it that? Because that is how we measured the rate of the change, but we needed to make it more accurate. How would I make it more accurate? I would just make the change as small as possible. What is making change small as possible? It is making it as infinitesimal. Okay? But not 0. Scientists before Newton and Leibniz, whenever they try to make this, they just put it as 0. So they encounter a case for which the denominator is 0, so they give up on the problem and say they couldn't make a progress in this case when they try to find the rate of change. But it was a new concept that Newton and Leibniz invented, which is the concept of infinitesimal, that made them able to calculate that rate of change. Okay? Now I'm dividing by a number that is not 0, but it is approaching 0. Okay? So in that case, we call it dy by dx. And that is exactly what we call the differentiation of the function. Now, in this case, I need to relate the concepts with each other. Geometrically, what would that represent? Now, what is delta x by delta y? Delta x by delta y, it is just the slope of this line. It is just the slope of this line. Okay? So whenever you make delta x approaching 0, what would happen to that line? It just keeps getting closer and closer to the point until that straight line just becomes a tangent. It becomes a tangent to that point, to the curve at that point. Okay? So what is the rate of change, which is dy by dx, which is the differentiation? It is exactly the slope of tangent. It is exactly the slope of tangent. So we are now relating several concepts to each other. several concepts to each other. That the rate of change is exactly the slope of tangent. And we call it the differentiation. Differentiation. We also call it derivative. And we denote it by these notations. We call it dy by dx. Also, we may denote it f dash of x, or we may denote it y dash. All of these are equivalent to each other. All of these are terminologies that are equivalent to each other. Okay? So, again, what is dy by dx, or what is the derivative? What I have done here, when I making a number or making a variable approaching some number, this is called, in mathematics, this is called a limit. This is called a limit. So, this is the limit of making delta x approaching 0 for that expression. Okay? When I want, before I just told you I'm letting delta x approaching 0. But the exactly, or the more formal expression for that, it is called the limit of that expression when delta x is approaching 0. We call it a limit. Okay? So that is called the differentiation. Now let's again re-express that expression. Make it in another expression. Now what is delta y? Let's remember what is delta y. Let's see that delta y. What is delta y? What is that delta y? It is the difference between these two values. Okay, so that is exactly f of x plus delta x minus the f of x. Okay, so this is exactly the definition of the differentiation. That is the definition of the differentiation. It is that limit defined like this. A differentiation or a derivative of a function at a point is exactly that definition. Okay? Now, as the concept of differentiation is have much of importance in our studies through the years of the faculty of the curriculum of the study of in our faculty of engineering, we will need to calculate the derivative for several kinds of functions, for several types or kinds of functions, or different forms or different expressions for the functions. So how would we do that? First, let's see what is meant by that definition. Let's try to find the derivative for a function, a simple function called x squared. Okay, let's try to find that. Let's try to find the derivative of that function. So what is the derivative? dy by dx, which is f dash of x. It is the limit of delta x approaching 0 for f of x plus delta x. What is f of x plus delta x in this case? Now this is just an expression for how f operates on its input. What does it make on its input? It squares it. So what would it do to that input? It would just square it. So x plus delta x all squared minus the f of x. I'm just applying the rule. F of x plus delta x minus f of x. So I write here minus x squared. All of that divided by the delta x. Okay? Now if I expand that expression, I would find it to be x squared plus 2 delta x x plus delta x all squared minus x squared all over divided by delta x. That term would be cancelled with that one, so I would find delta x approaching 0 of 2 delta x plus delta x whole squared over delta x. Now, if I try to substitute with delta x equal exactly to 0, I would find that this will give me 0 over 0. Now, this is in mathematics called unspecified quantity. Unspecified quantity. Why it is unspecified? Because these are not exactly zeros. These are not exactly zeros. They are infinitesimals. They are infinitesimals. So dividing an infinitesimal over an infinitesimal, we have just learned that infinitesimals are dynamic numbers. So by itself we can't know what would that value be unless we have known the rate at which, or the speed at which, this value is at this infinitesimal approaching the 0. So for example, I may have the numerator infinitesimal to be 0.00002 and the denominator infinitesimal at that same time it will just be 1. So what would be the ratio in this case? It would just be 2. Okay, so that's why it means that the speed by which you are approaching 0 for the numerator infinitesimal, it is just double the speed by which you are approaching the 0 for, or maybe no, it is the half of the speed. This is double the speed. So that's why the ratio between these two is just 2. That above number it will be larger, as if it is larger compared to the denominator, the infinitesimal of the denominator. Okay, so that's why this quantity is called unspecified, because if I give you calculate 0 by 0, you can't tell me without knowing how each of these infinitesimals are approaching 0. So how would I know the speed of each of these two infinitesimals approaching 0? It is by these expressions. Okay, now this is just to know the concept of that expression when you encounter it. But if you need to calculate it, in this case, for example, where you know how each expression of these, of the numerator and denominator, approaches the 0, it means when you find 0 by 0, it means that there is some factor that would be cancellated between the numerator and denominator. If you look closely at this expression, do you find any cancellation between the numerator and the denominator? Can you see any simplification or maybe cancelled between the numerator and denominator? Yes, I may find that. I may take delta x as a common factor from the numerator, and it would be cancelled with the denominator. So that would be cancelled like this. So what is the result in this case? It will just be delta x approaching 0. It will be 2x plus delta x. Now after making the cancellation, whenever I found that unspecified quantity which is called 0 over 0, I know that there is some cancellation that would happen between the numerator and denominator. After making that cancellation, I would just make a direct substitute in the expression. That would give me the value of that limit. So what is the value in this case? It would just be 2x. Okay? So I'm just here giving you a sketch of how would we find the derivative of a function using the basic definition of the derivative. But all of that we are not, or we will not encounter all of that in our study. We'll just take it as a table. We'll know it as a table. We can find the proofs by using limits in any sum textbook, but we will just study it as a table. We are just concerned more about applying these concepts instead of knowing the proofs of them. Okay, so now we can construct a table for differentiation. We'll construct a table of differentiation. I'll give some functions like this, and I will write the derivative of that function. First, what is the derivative of a constant function? A constant function is a function like this. It is a function like this. What is the change? Does any change happen in the y in this case? For a constant function like this, if you change in x, does any change happen for y? No. So what is the rate of change in this case? It is 0. So that's why the derivative of a constant by itself is just 0. The derivative of a constant is just 0. We also know the derivative of a power function. What is the derivative of a power function? That is just much like this case. What is the rule? What is the general rule for that? It is taking down the power, then subtracting 1 from the power. Okay, taking down the power, then subtracting 1 from the power. Okay, now this rule applies for any n. This rule, whenever it is positive or negative or a fraction or non-fraction or any it was, but you can apply the rule. For example, if I had, for example, root x, what is the derivative of root x? What is root x? When you express it, it is x power negative half. It is x power negative half. So what is the derivative? I will just apply the rule. I will take the power down, then x, I will just subtract 1 from that. That is the power of x power half, not negative half. It is x power half. So to find the derivative of that function, I will just take the power down to be half x, but power, I will subtract 1 from the power. It will be negative half. That is exactly, it may be re-expressed as 1 over root x, 1 over 2 root x. 1 over 2 root x. So that's why it is memorized. As we use it extensively, we know that root x, its derivative is 1 over 2 root x. Okay? One other expression that is used extensively, which is 1 over x. What if I need to find the derivative of 1 over x? What is 1 over x when I write it? It is x power negative 1, yes. So in this case, I will take the power down, so it will be negative x power. I will subtract 1 from the power, which will be negative 2. So what is that? It is negative 1 over x squared. So it is a memorized rule, which I say that 1 over x, its derivative is just minus 1 over x squared. And it is memorized like this as we use it extensively in our problems. Okay? Now this is the most important rule, which is the rule of the power function. Okay? Also we have the rule of the exponential function. The exponential function, it is a very special function, as its derivative is exactly itself. And that's why, and that is what characteristic for what characterizes that number e. Why have we chosen that e? We remember that e was 2.71. It is some number like this. What characterizes it? It is the only constant for which we make it the base for the exponential function, for which its derivative is itself. Okay? It is the exact number that makes this function its derivative is itself. That is what characterizes the constant or the natural number e. Okay? But if I had, for example, another function like this, a power x, if I had another base instead of e, what would be the derivative in this case? The derivative will just be as it is also, but it will be multiplied by the ln of the number that have taken the place of e, which is ln a. Okay, as if e power x is the standard form of the exponential function, and whenever you have changed the base to any other number a, I would just multiply to make that modification, or to to adjust that modification, I will just multiply by ln A. I will just multiply by ln A to find the derivative. Okay? Now also there is some other functions which is ln, which is the inverse of the exponential, So what is the derivative of ln x? It is 1 over x. The derivative of ln x, it is just 1 over x. Okay? So these are the basic functions that are memorized for the table of differentiation. Also, we have studied the trigonometric functions. So we will have a table for the derivatives of the trigonometric functions, which is like this: f of x, f dash of x. We have here sine x, cosine x, tan x, cotan x, sec x, cosec x. What is the derivative of sine? It is cosine. What is the derivative of cosine? It is negative sine. Okay? So we will note now that whenever you are differentiating a function with a co, you will put a negative sign in the derivative. Okay? So let's continue. Tan x, what is the derivative of tan x? It is known to be sec squared of x. It is, all of these rules are derived or have proofs, such as we have made for the limit, using the limit and so on. But we are just summarizing these proofs and all of these mathematics. We are just summarizing it in that table, so we can use it as much as possible. Cotan x, what is the derivative of cotan x? It is, now we are having a co in the function, so we are expecting it to will have a negative sign. What is the derivative of cotan? It is just minus cosec squared. Okay, so the derivative of tan x is sec squared, and the derivative of cotan x is negative cosec squared. Okay, what is the derivative of sec x? It is sec x tan x. And what is the derivative of cosec x? It would be cosec x, cotan x, but with a negative sign, because I have a co in this side. So whenever I have a co like this, the derivative would be a negative sign, Okay? Also, we have studied the hyperbolic functions. So let's write the table of hyperbolic functions. It is just the same as the trigonometric functions, but with a difference for the rule of the negative sign. Now, sine of x, cosine of x, tangent of x. These are the three basic hyperbolic functions. Then we will have the reciprocals of these three basic, which is the reciprocal of sine. It is just, or maybe the reciprocal of tangent is cotangent. The reciprocal of cosine is sec, and the reciprocal of sine is cosec. So these three are called the reciprocals. Okay? So what are the derivatives? The derivatives of the three basic hyperbolic functions are with a positive sign. Now we have a different rule for the signs. Instead of the rule of trigonometric, which whenever you are differentiating a function with co, you would have a negative sign. Now in this case we are finding that whenever we are differentiating a basic hyperbolic function, we will get a positive sign. What is the derivative of sine? It is just cosine. What is the derivative of cosine? It is just sine. What is the derivative of tangent? It is just sec squared. So what is the derivative of cotangent? Now these are one of the reciprocals, so the derivative would be with a negative sign. These three, the derivative of these three is with a negative sign. Okay? Now, in this case, What is the derivative of cotang? It is cosec squared x, negative cosec squared. What is the derivative of sec? It is minus sec tang. What is the derivative of cosec? It is cosec cotang. Okay, so now we have written the table, all of the table of the elementary functions that we have studied. Now you may notice that there are some missing functions that we have studied before. What functions are missing? Now are there any function that is missing from this table that we have studied? Constant, algebraic, exponential, ln, hyperbolic, and trigonometric. There are also the inverse functions, the inverse trigonometric and the inverse hyperbolic, sine inverse. Didn't we study the inverse hyperbolic, the inverse trigonometric, sine inverse, cosine inverse? All of these are considered to be elementary functions also, so we need to know how to find the differentiation of them. But we will postpone these functions to the next lecture, as we would depend on some rule to find the derivatives of the inverse functions. Now, this is the table of differentiation. This is the table of differentiation. These are the only functions that we could find its derivative? No. That's why we are not only restricted to the table, we will try to find rules to find the derivative of combinations of these functions in the table. We will learn how to find the differentiation of making combinations of the functions in the table. For example, there is a rule called the rule of sum and difference. The sum and difference. If I need to find the derivative d by dx of f of x plus g of x, if I have the sum of two functions, I need to find its derivative. It is just distributed on them. So it will be the derivative of d by dx of f of x plus the derivative of g of x, or we may say that it is f dash plus g dash, and so for the negative sign. So for example, if I need to find the derivative, of this function x power 3 plus x power 3 over 2 plus sine x. What is the derivative of this function? I will just make the derivative of each of them separately, then I add them up. Okay, so x cubed, what is the derivative of x cubed? We have just learned to take the power down, it will be 3x squared. What is the derivative of x power 3 over 2? I will just take the power down, it will be 3 over 2 x power x power, I will just subtract 1 from the power, it would be half. So sine x, what is the derivative of sine x? It is cosine x. Okay, so whenever I have a sum or a difference between functions, we just add or subtract the derivatives of these functions. Also, we have a rule for multiplying by a constant. If we have d by dx of c times f of x. Now, we have learned that the derivative of c of a constant function is 0. So, a constant by itself, its derivative is equal to 0. But if that c is multiplied by a function, what is the derivative in this case? It is just c, as if it is taken out of that operation. It is just c f dash of x, or d by dx of f of x. So that's why if I need to find the derivative of that function, for example, 3x power 5 minus 4 cosine x, I need to find the derivative of that function. So I just take it as it is, it would be 3. Then I would multiply it by the derivative of that function, which is 5x power 4. What about this? this constant, I just take it as it is, then I multiply it by the derivative of cosine x, which is negative sine x. So the resultant would be 15 x power 4 plus 4 sine x. So that would be the derivative in this case. Okay? Also, we have another rule which is called the product rule. Product rule. What is the product rule? The product rule, it is called if you need to find the derivative of two functions that are multiplied by each other. If I had a case like this, for example, x squared times sine x, what is the derivative of this function? I will not say that it is the derivative times the derivative. So if you say, for example, it is 2x times cosine x, this is a wrong answer. This is a known wrong answer. And this is one of the famous mistakes in this case. Okay, so what is the correct rule in this case? It is to write the first as it is, then you multiply by the derivative of the second. Then you take the derivative of the first multiplied by the second without a derivative. As if you are moving the derivative on both the functions I'm having here. Okay, so if I need to find the derivative, for example, of x squared sine x, what is the derivative? It would be like this. I will take the first as it is times the derivative of the second. What is the derivative of the second? It is cosine x. Then I add the other case. What is the other case? It is differentiating the first one, which is 2x. Then times the second one as it is, so it will be sine x like this. So that is the correct expression for the derivative of a product of functions. Okay? What if I had three functions that are multiplied by each other? For example, if I need to find the derivative of f times g times h. In this case, you just know that the derivative, you will only have one derivative that moves along each of the three functions. So the derivative in this case, it will be f dash gh plus f g dash h plus f g h dash. Okay, as if you are moving the dash or the derivative between the three, along the three functions that I'm having in the case. Okay. Now, for example, if I need to find the derivative of this function, if I need to find the derivative of x squared times 3 power x times cosine x, I need to find the derivative of this function. Now I am having three functions that are multiplied by each other. Three functions that are multiplied with each other. So I will use the first rule or the second rule? The second rule. We have three functions. So, and this rule can be generalized to any number of functions. If I have f, g, h, and so on, I will just move the dash along and move it along all of the cases that I'm having in my problem. So in this case, I will just make the derivative on the first, so it will be 2x, and keep the others as they are, plus the first as it is and the third as it is, times the derivative of 3 power x. What is the derivative of 3 power x? An exponential is the derivative of an exponential is the same as it is. But if I change the base to any other number than e, I just multiply by ln 3. I just multiply by ln of that number. Okay? Have I finished? No. Still I have the case for which the derivative is on the third factor, which is that one. So I'll be plus x squared 3 power x. What is the derivative of cosine x? It is negative sine. I'll just write it in a bracket like this, or I would take the negative sign with the sign of the term. Okay? What if I need to find the derivative of ln 3 times cosine x? What is the derivative of this in this case? Would I make it using the first rule or the second rule? Would I make it using the first rule, the first product rule, or the second product rule? What is most suitable in this case? Neither of them is suitable. In this case, I'm having a constant. This is a constant. So I'm having here not two functions multiplied by each other, but just one function multiplied by a constant. This is a different case from the product rule. In the product rule, I'm having two functions of x multiplied by each other. Okay? In this case, I'm having a constant multiplied by a function. And that is considered to be with this rule. I just take it as it is. That will be what is the derivative in this case? It will just be, the derivative will just be len 3. Take it down as it is and just multiply by the derivative of cosine x. What is the derivative of cosine x? It is negative sine x. So that is the derivative in this case. I don't add up two terms and so on as I've done in the product rule. No, I don't need to do that in this case. Okay? So this is the product rule. Also, we'll have another rule which is called the quotient rule. The quotient rule. What is the quotient rule? It is the rule for division of functions. For example, if I need to find the derivative of f of x divided by g of x, what would be the rule in this case? It is squaring the denominator. For the denominator, we'll just square it. And for the numerator, we will differentiate it. We will find f dash. So we will square whenever I have a denominator and denominator. I need to find the derivative. Its derivative, I would square the denominator and differentiate the numerator. Okay. Then I will complete the numerator as if it is like the product rule, but with a negative sign between the terms instead of a plus rule, instead of a plus sign. What is meant by that? F dash times g as it is, minus, in this case it is minus, and then I interchange the place of the derivative. So it will be f of x times g dash of x. Okay? So for example, if I need to find the derivative of x squared over sine x, I need to find the derivative of this function. Now I've just noticed that we have a function of x over a function of x. So this belongs to the quotient rule. So what would be the result in this case? I square the denominator. It would be sine squared x. Then I would differentiate the numerator. It would be 2x. Then I complete the numerator by using just in a form that is like the form of the product rule, but with a negative sign instead of a positive sign. So it will be, I've just differentiated the numerator. I'll just multiply it by the denominator as it is. It is sine x like this, minus the numerator as it is times the derivative of the denominator, which is cosine x. So that is the derivative in this case. Okay? So we have learned how to find the derivative of constant times a function, function plus a function, function times a function, and function divided by a function. Okay? There is also another case, which is the composition of functions. What if I had a function like this, f of g of x, a function inside another function? When I have a function inside another function, how would I differentiate it in this case? Now this case has a rule. It is called the chain rule. It is called the chain rule. What is the rule? To find the derivative, I would just take the outer function, which is f in this case, and I differentiate it, preserving what is inside it as it is, g of x. Preserve what is inside it as it is, so I'll just write it g of x like this. So in this case, I've just finished the f. I will go inside it and I will multiply by the derivative of what is inside it. So I will multiply by the derivative of what is inside it, which is g dash of x. That is called the chain rule. That is called the chain rule. So for example, if I had this function y is equal to sine x power 3, I need to find the derivative of this function. I need to find the derivative of this function. So I've just noticed that x3 is inside the sine. Now this is not a multiplication. Don't apply the product rule in this case. This is not the case of product rule. It is not sine x times x cubed. No. It is an x cubed inside the sine. The sine is operating on x cubed. So it is composition of functions or the chain rule. What is the rule in this case? I will just take the outer function and I differentiate it. What is the differentiation? What is the differentiation of the sine? It is cosine. So I will write it cosine and I preserve what is inside it as it is. So it would be cosine x cubed. It would be cosine x cubed. Now I have just finished that outer function. So I will go inside it and I will find x cubed. What is the most outer function in this case? Which is x cubed or power 3. What is the derivative of this function? It is just 3x squared. So I'll just multiply it by 3x squared. Okay? So this is how I would apply the chain rule in this case. What if I told you I need to find the derivative of this function? Sine cubed of x instead of sine x cubed. I need now to find the derivative of sine cubed of x. Now remember, what is sine cubed of x? It is just sine x all power 3. Okay? So what is the outer function in this case? What is the most outer function in this case? It is cubing. Cubing. And what is the derivative of cubing? What is the derivative of cubing? What is the derivative of x cubed? It is taking the power down and take it as it is, then make it over power 2. So that what I will do here, I will just take that 3 and leave what is inside it as it is. Preserve it as it is. So it will be sine x like this. Then I subtract 1 from the power. It would be 2. Now I have just finished the outer function, which is power 3. I would go inside it. What is inside it? I will find sine x. What is the derivative of sine x? I will just multiply this by the derivative of sine x, which is cosine x. So that is the derivative in this case. You just as a notice, there is another form for the chain rule. Just an equivalent form. It is just an equivalent form for the chain rule. I prefer that form. I see it more applicable. But you may encounter some other form like this. Y is expressed as a function of t, and t is expressed as a function of x. Now, in this case, I may find the derivative of y with respect to t. And I would find the derivative of t with respect to x. But I need to find the derivative of y with respect to x. What would it be? It would just the derivative of some path. It is just the multiplication of that path. It would be dy by dt times dt by dx. Now this is just equivalent to that form. How is it equivalent? If you, for example, name this function as t. Now we have t as a function of x. So we'll have y will be as a function of t. What is dy by dt? It is just f dash of t. That is exactly f dash of t. So what is g dash of x? It is t. This is the derivative of t with respect to x. So that is exactly g dash of x. So this expression is just the same as that expression. That is f dash of t, which is this one, dy by dt. And then g dash of x, it is the derivative of t with respect to x. g dash of x, it is the derivative of t with respect to x. So they are just two equivalent expressions for the chain rule. Now what if I need to find the derivative of this function? For example, y is equal to x cubed plus 5x squared all power 6. What is the outer function in this case? It is, what would be the last operation when you need to calculate this expression? What is the last operation that we do? You would make it power 6. That is the last operation. So that is the outer function. It is power 6. So that is why I would start the differentiation process. So I will just differentiate power x. What is the differentiation of power x? Take the power down, preserve what is inside it as it is, subtract 1 from the power, which would be 5 in this case. Now I have just finished the outer function. Then I would go inside it. When I go inside it, I would find a 2 terms expression. So in this case, it would just be like this. Whenever I have more than one term added up, I would make a bracket like this, and for each of them I will find the derivative of each term. So in this case, x cubed, it is just the derivative would be 3x squared. So what is the derivative of 5x squared? It is 10. I just take the power down, it would be 10x. Now I have finished all of that, so that is the derivative of that function. So what if I need to find, for example, the derivative of that function? Root of x squared plus e power cubic root of x. This is cubic root. What is the outer function in this case? It is the root. It is the root. What is the derivative of root? 1 over 2 root. So that is the rule that I will apply. 1 of the 2 of double of the root, and I will keep what is inside it as it is. So x squared e power cubic root of x. Now I have finished the root. Now look, as you notice, every step I make it for me not to confuse. I just every step I just make a scratch like this to know that I have finished that function. And that's striking out. I'm just making it in the original function, not in the function here, for example. Okay? In order not to confuse when applying the derivative or applying the chain rule, you need to know what you have finished. Then go inside each one you have finished. Now, I've just finished the root. I will just multiply it. Okay? When you apply the chain rule, they are terms multiplied by each other like this, as if they are levels. As if they are levels, or each one multiplied by each other. Now, whenever, if I have finished the root, I will go inside it and I will find this function. This function is composed of 2 terms. So, I will just make a bracket like this and put a plus sign like this. So that will be 2x. The derivative of x squared is 2x. So what is the derivative of e power? This is the second function. That second function, I will find the exponential. That's the outer function. It is exponential. If you need to compute that number, if I give you some number, e power, for example, cubic root of 2, how would you compute it? You would compute that first, then the last function that you will operate on, which is e power that number. So that is the outer function. It is that e. What is the derivative of e? It is as it is. So I will just write it as it is. I have just finished the exponential. Then I would go inside it. Then I multiply by the function that is inside. Now I have the cubic root of x. What is cubic root of x? It is x power 1 over 3. It is x power 1 over 3. So in this case, what will be the derivative? I will take the power down. It will be 1 over 3 times x. I will subtract 1 from the power. It would be negative 2 over 3. So that's why I will just write it as 1 over 3 x power negative 2 over 3, and that I would finish the function. The derivative is complete. Okay? Now, if I need to find, for example, the derivative of that function, y is equal to ln of 2 plus sine 3 power x. Now let's apply. If you apply the rules as I have told you, you will not get confused. Okay? Just apply the rules as I have told you. I need to find y dash. What is the outer function that I will counter in this case? It is that ln. What is the derivative of ln? It is 1 over what is inside it. It is 1 over what is inside it. So that ln, what is the derivative? What is its derivative? It is 1 over what is inside it. So now I have finished that ln. I would go inside it. Now I will just multiply by the derivative of what is inside it. Okay? Now, just you need to notice, I'm not looking here. I'm not looking here. I'm looking in the original function. Okay? So that function is finished. What is inside it? It is that function. What is the first function that what is the last function that I will counter here? It is, what is the outer function? It is also that ln. What is the derivative of that ln? It is 1 over what is inside it. So now I have finished that ln also. I would go inside it times what is inside the derivative of what is inside it. I would find two terms. I would write these brackets like this and write it like this. The first term, what is the derivative of 2? What is the derivative of a constant? What is the derivative of a constant? It is 0. The derivative of constant is 0. I need you to participate with me. You are not listeners here. You need to participate in the lecture. So now we need to find the derivative of sine 3 power x. What is the derivative of sine? It is cosine. The derivative of sine is cosine. So I finished the sine. I will go inside it and I will counter 3 power x. What is the derivative of 3 power x? It is, now, no, this sine, I will just keep what is inside it as it is. Okay? Sorry. Let's make that again. I need to find the derivative of sine 3 power x. What is the first function? What is the outer function? It is sine. What is the derivative of sine? It is cosine. And I will keep what is inside it as it is. So it will be 3 power x. Now I have finished that sine. Then I will multiply this by the derivative of what is inside it. What is the derivative of 3 power x? It is as it is, 3 power x, but multiplied by ln 3. Now, what is the derivative of 1 over something? We have just learned before. What is 1 over something? It is that something power negative 1. So what is the derivative of 1 over something? It is just taking the negative down, then taking that negative 2, or which we write it as negative 1 over that something squared. So the derivative of 1 over something, it is minus 1 over that something squared. This is a rule for us that we may use it extensively in our problems. For example, if I need to find the derivative of that function, y is equal to cosine of 1 over ln root x plus e power x squared. Now, for this case, what is the outer function? It is cosine. This is cosine of all of that. So, the derivative, it would be, what is the derivative of cosine? It is sine. And I will keep what is inside it as it is. Times the derivative of what is inside. What is the outer function in this case? Would it be ln? No, it is not ln. What is the outer function in this case? It is 1 over something. It is power, all that power negative 1. It is the power negative 1 in this case. So, what would I would multiply it by? I just told you that 1 over something, the derivative is negative 1 over that something squared. So, this function is, the derivative, it is minus 1 over that ln all squared. Now I have finished the 1 over function. The derivative of 1 over function, I have just written it like this. Now I would go inside it and I would find this function. That is inside, this is what inside that. So I need to multiply by its derivative, the derivative of what is inside it. What is the first function that I would encounter in this case? What is the outer function? It is the ln. What is the derivative of the ln? It is 1 over what is inside it. So it would be 1 over what is inside it. Now I have just finished the ln. Then I would go inside the ln. I would find this function. I will find it composed of 2 terms. So I will just write brackets like this. Let's write the brackets like this. Root x, which I know its derivative, it is 1 over 2 root x. And for the second term, it is e power x squared, which would be e as it is, e power x squared. Then I will go inside it. I have just finished the e. I will go inside it. I multiply it by 2x. Okay? So this is how we apply the chain rule. This is how we apply, and we have seen many examples in this case. Do you know how to write the equation of a straight line? Or maybe okay, there is something called higher derivatives. Higher derivatives. It is a simple concept. It is making the derivative more than once. For example, if I had a function f of x equal, for example, x power 5. Okay, the first derivative, it is f dash of x, which is 5x power 4. We denote this as dy by dx. Now, if I make the derivative of the first derivative, what we would call it? We would call it the second derivative. We would call it the second derivative. What is the second derivative? We denote it by f double dash of x. So we just make a derivative for that function. It would be 20x power 3. And we need, how would we denote it in this form? It is denoted like this, d2y by dx squared. Why did we denote it like that? Why didn't, for example, now look at this expression, d2y by dx squared. Why didn't we, for example, write it d2y squared dx squared, or for example, d2y by d2x? No, this expression is based on some idea, which is that we consider the dy by dx as the differentiation operator operating on y, like this, as if this is an operator, operating on that y. So if I operate again another dx, d by dx, the differentiation operator, if I operate it again, I may look at these two at a single operator like this, d by dx all squared, operating on y. Then we distribute that squared like this, it would be d2x squared like this. It is known to be dx. So this is this form, it is d2y by dx squared like this. But instead of writing the brackets like this each time, we just write it as d2 by dx squared like this. Okay? So this is called, or this is the notation of the second derivative. So if I complete in the same manner, I will just find it f triple dash of x, it will be 60x squared. That is d3y by dx cubed. If I need to find the fourth derivative, it would be 180x. I will just not write it f4 dashes, no, I will just write it as 4 in brackets like this, and it would be d4y by dx power 4. Okay? So this is the concept of the higher derivatives. Okay? Then we'll complete in another lecture.